Download this code from codegive.com, link in the description below. All hope is not lost, your deliverer is on the way, building resilient and fault-tolerant applications. This tutorial will guide you through the concept of resilience and fault tolerance in software development, focusing on building applications that can withstand failures, gracefully degrade, and recover without significant downtime. We'll explore various techniques, design patterns, and code examples in Python to illustrate these principles. We'll emphasize the idea that even when things go wrong, you can architect your application so that all hope is not lost and a deliverer, in the form of robust recovery mechanisms, is on the way. Understanding the need for resilience and fault tolerance. In today's complex and distributed systems, failure is inevitable. Think about the potential points of failure in a typical web application. Network issues, intermittent connectivity problems, DNS resolution failures, packet loss. Hardware failures, server crashes, storage device failures, network card malfunctions. Software bugs, unexpected exceptions, resource leaks, deadlocks. Third-party dependencies, downtime or performance degradation of external services, APIs, databases, message queues. Human error, accidental misconfiguration, incorrect deployments, unintentional data corruption. Resource exhaustion, memory leaks, CPU overload, disk space filling up. Security breaches, denial of service attacks, unauthorized access, data corruption. Without proper resilience measures, these failures can lead to downtime, application unavailability, impacting users and potentially leading to financial losses. Data loss, corruption or permanent loss of critical data. User frustration, poor user experience due to errors, slow performance, and unreliable service. Reputational damage, loss of trust in the application and the organization behind it. Resilience is the ability of a system to adapt and recover from failures. It's about ensuring the application continues to operate, albeit potentially in a degraded state, even when problems occur. Fault tolerance is a specific aspect of resilience, focusing on designing systems that can continue operating correctly even in the presence of faults, errors or defects. This often involves redundancy, replication, and error detection/correction mechanisms. Our goal is to build systems that are available, accessible and responsive to users. Reliable, consistent and dependable in their behavior. Scalable, able to handle increasing workloads. Maintainable, easy to understand, modify, and debug. Testable, designed to be thoroughly tested for robustness. 2. Core principles and patterns for resilience. Here are some key principles and design patterns for building resilient applications. 1. Embrace failure as a normal occurrence. Don't try to avoid failure entirely. Instead, design your system with the expectation that failures will happen. 2. Single points of failure. Identify and eliminate single points of failure. Redundancy and replication are key strategies here. 3. Isolation. Isolate different parts of the system so that a failure in one component doesn't bring down the entire application. This can be achieved using microservices, process isolation, and fault domains. 4. Fail fast. Detect failures quickly and take appropriate action. Don't mask errors or try to continue operating in a degraded state without proper awareness. Raise exceptions, log errors, and trigger recovery mechanisms. 5. Retry with backoff. When a transient failure occurs, example a temporary network issue, retry the operation with an exponential backoff strategy. This avoids overwhelming the failing service and gives it time to recover. 6. Circuit breaker * prevent repeated calls to a failing service from consuming resources and potentially cascading failures. A circuit breaker monitors the success/failure rate of calls to a service and opens the circuit when the error rate exceeds a threshold. While open, calls are short-circuit and immediately return an error, preventing further attempts to the failing service. After a timeout, the circuit breaker enters a half-open state, allowing a limited number of calls to attempt recovery. 7. Bulkhead * isolate critical resources, example threads, connections, for different parts of the system. If one component is consuming excessive resources, it won't starve other parts of the application. 8. Timeout * set reasonable timeouts for all operations. This prevents operations from hanging indefinitely and consuming resources. 9. Health checks * implement health checks to monitor the status of your application and its dependencies. Use these health checks for automated recovery, scaling, and routing. 10. Graceful degradation * when a failure occurs, gracefully degrade the application by disabling non-essential features or providing a simplified user experience. 11. Idempotency * design operations to be idempotent, meaning that they can be executed multiple times without changing the state of the system beyond the first execution. This is important for retries and message processing. 12. Compensation * when a failure occurs in a distributed transaction, use compensation logic to undo any partial changes made before the failure. This is essential for maintaining data consistency. 13. Logging and monitoring * implement comprehensive logging and monitoring to track the behavior of your application and detect failures early. Use metrics, alerts, and dashboards to gain insights into the health and performance of your system. 14. Chaos engineering * proactively inject failures into your production environment to test the resilience of your system and identify weaknesses. 3. Code examples in Python. Let's illustrate some of these principles with Python code examples. We'll use the requests library for making HTTP requests and the tenacity library for implementing retry logic. First, install the libraries. 1. Retry with exponential backoff. Explanation ****. Add retry decorator ***. The tenacity library provides a convenient add retry decorator to add retry logic to functions. **stop** The stop parameter specifies when to stop retrying. Stop _after _attempt, 5, means retry a maximum of 5 times. **wait** The wait parameter specifies how long to wait between retries. Wait _exponential implements exponential backoff, where the wait time increases exponentially with each retry. Multiplier controls the rate of increase, min sets a minimum wait time, and max sets a maximum wait time. *retry The retry parameter specifies which exceptions to retry on. Retry _if _exception _type, requests.exceptions.request exception, retries only when requests.exceptions.request exception or its subclasses are raised. *requests.raise for status, this line is crucial for handling HTTP errors. It raises an HTTP error if the response status code is 4xx or 5xx. 2. Circuit breaker, simplified example. Explanation ***. Circuit breaker class ***. This class encapsulates the circuit breaker logic. State ***. The circuit breaker has 3 states, closed, open, and half_open. Failure _threshold the number of failures that must occur before the circuit breaker opens. Asterisk recovery underscore timeout asterisk the amount of time to wait before transitioning to the half underscore open state. Asterisk call, asterisk this method is used to execute the function. It checks the circuit breaker state and either executes the function, prevents execution, or allows a trial execution in the half underscore open state. Asterisk open, asterisk transitions the circuit breaker to the open state. Asterisk half underscore open, asterisk transitions the circuit breaker to the half underscore open state. Asterisk close, asterisk transitions the circuit breaker to the closed state and resets the failure count. Asterisk reset, asterisk resets the circuit breaker state. Only called after a successful execution of the protected function. 3. Timeout. Explanation asterisk. Asterisk timeout parameter asterisk the requests.get method takes a timeout parameter, which specifies the maximum number of seconds to wait for a response. Asterisk requests.exceptions.timeout asterisk if the timeout is exceeded, a requests.exceptions.timeout exception is raised, a subclass of requests.exceptions.request exception. 4. Health checks. Explanation asterisk. Asterisk check underscore service underscore health, asterisk this function performs an HTTP GET request to the service's health endpoint and checks the response status code. A 2xx status code indicates a healthy service. Asterisk monitor underscore service underscore health, asterisk this function periodically calls check underscore service underscore health, and takes actions based on the health status. It is run in a separate thread so that it doesn't block the main application. Asterisk threading asterisk using a threading.thread allows you to run the health checks concurrently without blocking the main application's execution. The daemon equals true setting ensures that the health check thread will be terminated when the main program exits. 5. Graceful degradation, conceptual. Explanation asterisk. Asterisk the get underscore user underscore profile function attempts to fetch the full user profile from the database. Asterisk if a database connection error occurs, simulated in the fetch underscore profile underscore from underscore database function, the function catches the exception and returns a simplified profile with limited information. This allows the application to continue functioning, albeit in a degraded state, rather than crashing or displaying an error message. 4. Beyond the basics, advanced techniques. Asterisk microservices architecture asterisk breaking down your application into smaller, independent services can improve resilience by isolating failures. If one microservice fails, it doesn't necessarily bring down the entire application. However, microservices also introduce complexity in terms of communication, deployment, and monitoring. Asterisk containerization, Docker, and orchestration, Kubernetes containers provide a consistent and isolated environment for running your applications. Kubernetes is a powerful orchestration platform for managing and scaling containers. Kubernetes can automatically restart failed containers, roll out updates with zero downtime, and provide self-healing capabilities. Asterisk message queues, RabbitMQ, Kafka message queues provide asynchronous communication between different parts of your application. If one component is unavailable, messages can be queued up and processed later. This improves resilience and decoupling. Asterisk service mesh, Istio, Linker to Service Mesh provides a layer of infrastructure for managing communication between microservices. It can handle traffic routing, load balancing, service discovery, and security. Service meshes also provide built-in resilience features like retries, circuit breaking, and fault injection. Asterisk database replication and failover asterisk replicating your database across multiple servers can improve availability and fault tolerance. If one server fails, the other servers can take over. Failover mechanisms automate the process of switching to a healthy replica. Chaos engineering experimenting with failures in a controlled way, such as randomly terminating servers or injecting network latency, is called chaos engineering. It helps you identify weaknesses in your resilience strategy before they cause real problems. Tools like Gremlin and Chaos Toolkit can automate chaos engineering experiments. Conclusion, all hope is not lost, your deliverer is on the way. Building resilient and fault-tolerant applications is crucial for ensuring the availability, reliability, and scalability of your software. By embracing the principles and patterns discussed in this tutorial, you can create systems that can withstand failures, gracefully degrade, and recover without significant downtime. Remember that failure is inevitable, but with proper planning and implementation, all hope is not lost. Your deliverer, in the form of robust retry mechanisms, circuit breakers, health checks, and other resilience strategies, can ensure that your application stays up and running, even when faced with adversity. The key takeaways are: design for failure, assume failures will happen and build mechanisms to handle them. Isolate failures, prevent failures in one area from affecting others. Automate recovery, use tools and techniques to automatically detect and recover from failures. Monitor and test, continuously monitor your system's health and test its resilience through chaos engineering. Iterate and improve, resilience is an ongoing process. Continuously learn from failures and improve your resilience strategy. By adopting these practices, you can build applications that are not only functional but also robust, dependable, and able to weather the storms of a complex and unpredictable environment. Your users will thank you for it.